Once you start looking, they are everywhere. Bamboo, honeycomb, termite mounds, chameleon eyes. We are surrounded by exquisite examples in nature where materials have been developed into incredibly effective forms and structures. Tens of millions of years of iterative evolutionary tinkering has generated sublime variations using the same materials again and again. Well, humans are now beginning to make our own designs, and we call them architected materials. And they are changing the face of what is possible in manufacturing. Let me show you what I mean. This is ASU. We tend to think of materials as the stuff that makes up the world around us. Materials like steel, rubber, and ceramic. We then shape these materials into products and objects we can actually use, like bridges, tires, dinner plates. And the reason we choose a particular material for a particular product is that the material in question has some properties that the product needs. Bridges need to be strong enough to resist the load of passing traffic. Steel is a strong material for this purpose. Tires need to absorb energy and provide grip. Rubber has the necessary compliance to do this. Dinner plates need to look good after repeated use. Ceramics are hard and resist scratches. Over the past several decades, hundreds of new materials have been developed with improved properties for these kinds of applications. But did you know that there is a way to make a material that is not just about the material itself? It involves designing the material in such a way that it acquires different properties on account of not only its basic composition, but also its design. We see this principle in nature a lot. The same materials are used in different ways, as evolution has led adaptations by different organisms in new directions. Beeswax to make honeycomb, soil and saliva to make termite structures, the dermal scales of shark skin. Now, in engineering, we call these architected materials. Why? Because we now are architecting the structure of these materials towards achieving certain properties. And this is the important part. These properties cannot be obtained using the material itself. Doing this often gives the material a new behavior that it didn't have in its intrinsic state. And that is why we also refer to these materials as metamaterials. In a way, we transcend the limitations of the material by exploiting design. The convergence of two technologies, 3D printing and computer-aided design, or CAD, has boosted the interest in architected materials. Prior to the advent of 3D printing, we were limited to fabricating honeycombs and foams, the kind you find in packaging materials used in shipping goods across the world. But with 3D printing, we can now create complex geometries at small enough sizes where we can influence the behavior of a much larger structure. The question then is, how do we design these materials and this larger structure? Enter CAD. With modern CAD tools, it is possible to fill in a three-dimensional volume with a wide variety of architected materials. Architected materials are, broadly speaking, either honeycomb-like, two-dimensional designs that are extruded in the third direction, or true three-dimensional structures made of beams or surfaces. Beam-based architected materials are typically called beam lattices. Surface-based architected materials are normally derived from mathematical functions and take on a wide range of forms, such as the gyroid and Schwartz P. Now you may ask, Why should we care about architected materials? There are several reasons. Firstly, they have the potential for reducing the amount of material we need for a given product, so they can enhance sustainability. Secondly, by manipulating design at smaller scales, we can achieve multiple functions in the same component. Consider the bones in our bodies. They provide structural stiffness and strength. They provide protection to our internal organs, and they absorb energy, all while serving as storage sites for important minerals and having the lowest mass possible. A key reason bone is able to do all of this lies in how it exploits architecture and how that varies across the body. The architecture in nature is frankly very impressive. Architected materials have so much scope to help us live. The next generation of safety helmets can use these designs, for example, to add another layer of protection for the human brain, in addition to the skull, whether that is for base jumping, hockey, motorsports, military, or space travel. In many cases, it is the science of architected materials that is allowing us to develop new structures that tolerate and absorb impact and strain, mimicking and improving on natural designs in the places we need them. This was ASU. Thanks for watching.